Yeah, so I'm Willem. I'm a postdoc here at TAL. I'm going to talk to you now about a little sort of a grab bag of different techniques and tools that I've been working on using delay logs and different machine learning techniques to sort of provide some potential operation support for passenger railways. The key sort of kernel of this research is a data set. It's a data set of railway delay logs. When I say railway delay logs, I mean that when there is a delay on the railway, the incident or the log is recorded with some metadata, so information about obviously where the location happened, what trains were involved. There's often a delay code, which we can translate into a topic or cause. So a delay code is usually business oriented, but a topic or cause is a little bit more, more cause oriented, as you can see. And of course, the delay information is recorded, the amount of delay that was incurred. So I'm going to use two different words throughout this presentation. I'm going to use events and I'm going to use incidents, and I'm going to hope I don't confuse the two. Events are specific single incidents of delay, so single occurrences of a delay. So if a train, for example, is having a lot of passenger volume and it's becoming increasingly delayed and it's incurring multiple delays from station to station, we can bundle those events together into a single incident. So basically an incident is one or more events. And we'll talk a little bit about what we can do with the two of those in terms of some of these tools. This data also includes, and we'll talk about that later, a remarks section. So there's lots of metadata that's recorded, and then there's also sort of a free text remarks thing, which is common in many different agencies, and it allows the user to just describe a little bit the story of what's happening or some of the root causes that may not be captured by the metadata. The goal here is to use this data set to look a little bit at where delays occur on the network, what types of delays are most common or largest, how these delays are connected to each other, or how locations on the network are connected to each other through these delays. And then we want to see if we can provide some historical context, some sort of institutional knowledge about an emerging incident. So provide some evidence from the past or some information from the past. And then, of course, we want to try and make some predictions about emerging incidents. And so I'm just going to run through a bunch of results of those. We won't get too much into the methods. First, just to give you a bit of context, if you're not familiar with the GO Rail network in the Greater Toronto Hamilton area, 69 stations, there's 8 branches, there's sort of 8 arms that all culminate and meet together at Union Station. So Union Station is this critical node, one of the busiest passenger railway stations in North America. So first, some quick summary stats. Here we're looking at topics on the right. Topics are, again, the mapping of these delay codes onto sort of fairly specific types of delays. As you can see, priority given to another train, either if a train is lined ahead, for example, a VIA train, or if a train ahead breaks down, like a freight train is ahead and it breaks down. Anytime a train gets in the way of the train that is delayed, it's categorized as that. Signal failure is another big delay cause as well. And by the way, these are average yearly delays over the course of 5 years, which is about where we're dealing with about 70,000 data points or 71,000 data points. As you can see, construction and passenger boarding and alighting also cause a fair bit of delay, but those incidents are less, they don't take as long, but they're more frequent. So there's always this trade-off. If we group these topics together into themes, there's a couple of things that stand out. So in terms of average event delay, so the delays that take the longest to resolve on average, safety-related ones, as you would expect, and weather-related ones, as well as track and way, such as signal and switch failures, take a long time to resolve. Whereas, as I said, system volume and procedural ones, such as a platform overshoot, are much smaller. And so when you combine all those things together, people-train conflicts, which is basically anytime a person or the outside world interacts with the train system in a way it wasn't supposed to, so crashes, trespassing, vandalism, passenger alarms, false alarms, things like that. All of that is people-train conflicts. Traffic conflicts, which we discussed in track of way, are sort of the big culprits. So one of the things we can do with this delay data, since we've bundled events into incidents, is we can basically look and connect two locations together on the network. We can draw a line between two locations if they both share an event. So if a delay includes both of those stations. And the thickness of that line can be the total delay that is shared between those two stations. And from that, we can draw a graph. And we can use some graph analysis techniques to learn a little bit about different features of that type of sort of delay graph. Here you can see location pairs at the top chart. So for example, Union Station and Aldershot Go, which are the two terminal stations of the Lakeshore West line, share a lot of common delay. So if there's a delay on that entire corridor, it will affect both ends of that a fair bit, or it will affect departing delay at both ends of that. Similarly, Union Station Oshawa terminal stations at the busy Lakeshore East line as well. There's some other interesting overlaps: Port Credit, Go, and Credit. So two locations that are the station and the nearby, I believe, yard or nearby interface. So delays are often connected through those as well. It happens at one and it affects the next one as well. We can look at something called degree similarity, which is a little bit to sort of a measure of how much a node acts as an influencer. We heard a little bit about some Twitter analysis earlier. Again, Union Station, that hub node, stands out, as well as the two terminal stations on the Lakeshore West and East lines as well. Another interesting one is betweenness similarity. Betweenness similarity looks at basically how much a node acts as a go-between between two other nodes, so as a bridge, so to speak. And so here you can see locations that are often sort of in the middle of a delay. So they're involved in a delay, but they may not be where the delay starts or ends. So just lets you sort of paint a picture of your network a little bit and how delays work on it. Another thing we can do is we can use this sort of free-form text remarks that are made by usually the dispatcher and do some topic modeling. Topic modeling is a machine learning technique where we find sort of keywords or important words, here kind of stemmed and bolded in these three examples of free-form remarks. And then we can do some analysis on how frequently they occur and how frequently they occur together to start getting these bundles of words. It's sort of like I like to describe it as a word cloud on steroids. And you can see you can get these bundles of 5 words here shown. There's 5 examples. Each row is a group. So the top row, overshoot, platform, reverse, required foot. You see it's bundling together occurrences where there's a platform overshoot and the train needs to reverse and there's a delay because of that. In the middle, we have via, late, wait, follow train. So this is when a via train is running late and a go train is required to follow it. And so it is also then delayed. And this can help you determine some of the categories in your data if you don't already have them categorized, or it can help you look at things like miscellaneous categories and learn a little bit more about what's common in those ones as well. The next thing we can do is we can create a recommendation system or a recommender for historical events. This kind of works the same way that Netflix does when it recommends what you should watch next based on what you seem to like. Basically, what we take is an emerging event, which is the top row here, and we take the metadata that would be provided, so we know where the delay is and what's going on, the temperature at Pearson, the topic of the incident or of the event, and we can try to match it up with anything in the past, in this case, the past 5 years worth of data that shows up as a good match. And in this case, we do that using a technique called cosine similarity. And this lets you maybe show the top 10 best matches. You can see the top row of the results is a pretty good match. There's lots of bolded matches, but some of them are less of a good match. And so if we can provide, for example, the top 5 or the top 10 historical events that are similar, a dispatcher can look at the remarks, can look how things were responded, can look how long it took, can learn a little bit about the circumstance, and perhaps use that to sort of supplement their existing institutional knowledge about the system to make better decisions and maybe resolve the incident a little bit faster and smoother, and also improve communications about it. And of course, the last thing that I've been working on is making predictions. The big question is, can we use information about an emerging event? So, we get a report of an event happening. Can we make some predictions about how much delay that's going to end up resulting in cumulatively? So broken switch, can we figure out how much a broken switch at Oakville Go is going to result in? There are, at the bottom, we have a little bit of results of some various types of ways of predicting. The machine learning technique we used here is random forest regression. The score, the mean squared error score that you're looking at is lower is better. And then there's three sort of naive ways of predicting that I have compared it to. One is to just take that delay and assume it's going to stay the same. So it was 5 minutes late at that point. We're just going to assume the delay was 5 minutes. The other is to take the median delay across all the delays. So just assume a median or assume a mean. And as you can see, by basically taking a baseline of initial delay and tweaking it a little bit based on different characteristics, we can learn a lot more about, we can get a little bit better at predicting what the resulting delay might be. And on the top right, you can see a graph of which factors the model decided were important. So obviously that initial delay, very important factor. And then different yes or no flags, whether or not it was a signal failure, whether or not it was a rule violation, whether or not it happened at Oakville Yard, all impact its decision on how much delay there's going to be. And then the hour and the temperature at Pearson are also influencing factors as well. So some of the next steps are to combine this delay logs with some potential location-based data, such as GPS, try and look at network effects and how delay propagates throughout a network. So how do knock-on effects work throughout this entire, all eight branches of this network together, and do some response scenarios with some historical incidents, and maybe develop some on-the-fly prescriptive methods so dispatchers can see the potential outcomes of their different choices they may have as an event starts to turn into an incident. And that's everything. Thanks, of course, big thanks to Metrolinx for providing the data and the support and the expertise on the data and the operations. Thank you.
Thanks a lot, Willem. I know it's a lot of data that you've been working with. 5 years worth of delay logs. That's so much really to cope with. One of the comments you made or observations you made was delays caused by VIA trains. I know separately you've done some work analyzing reliability of VIA. Can you tell us something about really the difference or what really major observations and conclusions you found on your analysis of the reliability of VIA trains?
Well, the upshot is that VIA struggles with reliability. And it also seems to be the upshot that in many cases, it's not exactly their fault. It's often a result of the infrastructure that they're on, interaction with other trains. They interact with freight trains, I think, even more on average than a GO train does as well. So certainly as everything converges, as all the trains converge on Union, they're going to start interacting with each other. And if they're all more reliable, of course, that makes everything a whole lot easier. So I can imagine that there's, I can't speak for Metrolinx, but I can imagine that there's plenty of motivation to have both of these rail systems be reliable and not interfere with each other.
Good. Well, thank you so much. Again, a reminder to everyone, if you have questions to any of the speakers, please add them to the chat box and the speakers will respond promptly.